In section 4.9, we're going to take a look at solving polynomial inequalities. And this is really very much so like when we solved normal inequalities, but for these problems we have to use a number line where we're going to test points instead of just graphing a number line solution. So if we think back to when we did linear inequalities and we tested a different point on the side of the line on the graph, that's the same idea here. So what we're really going to end up doing is we're going to factor the inequality statement the same way we factored a polynomial. We're going to find the roots of this inequality, but we're going to call it the critical points. Okay, critical points, one of our key words. And then once we have our critical points, we're going to take those regions. So let's say critical point, or the root 1 is, let's say, -2, and root 2, or the second root, is +3. If those are the roots, we're going to put this on this number line. We're going to call these critical points. These are the critical points in our problem. And we're going to test the regions that are created by evaluating one of the members in the inequality. So we're going to have an inequality statement. We're going to have something with x in it. And it's going to be x squared, obviously, at least here, because we're polynomial. We're going to have, like, say, greater than 0. So we're going to pick a point. So we would pick a point over here, and let's say the point maybe is like -5. Anything to the left of -2, really. So we pick -5. And if we go ahead and plug -5 into this expression, we need to see if it's positive or negative. So let's say we plug -5 in here, it turns out to be negative. And then we go ahead and we take a number that's in here. Well, what number in here is easy to plug into an expression? Well, 0. 0 is right in here somewhere. Plug a 0 in up here, and let's say we get a positive region here, or we get a positive symbol. And then finally, on the far right, let's say we pick a number greater than 3, like a number like 7. We plug 7 into this expression, and that comes out to be negative. Well, the question is, where's our answer? Which of these 3 regions? Is it one of the regions? Is it 2 of the regions? Is it all 3? Is it just 2 out of 3 of them? Like skipping one of them? Well, what we have to do is go back to our original statement and say, the question was asked really, when is this expression greater than 0? Well, when things are greater than 0, they are positive, and therefore we're looking at this region. So the solution set is in that region. Now, this happened to just be greater than, not greater than or equal to. So what we do is we put open circles here and here, because it was just greater than. And now because our region in the middle is our solution region, because it's positive or greater than 0, remember, greater than 0, or this region is positive, we go ahead and we shade in here. And then we have to take our graph and just turn it into a solution set. So we'd say that x is in the set of numbers between -2 and 3. Okay, so we have an AND statement there in a sense. Had this sign here, instead of being greater than, been less than, like this, had it been a less than symbol, we wanted to know when is this expression here less than 0 or negative. So the answer key would have been the opposite locations. It would have been this region and this region. And that would have been an OR statement. We'd have to write that as x is less than -2, or x is greater than 3. So again, it would change based on what the question asked, but this was a hypothetical question right here, where when this was solved for the roots of it, we got these roots, also known as our critical points, which end up becoming like our barriers, in a sense, for the solution set in this problem. Example 1 says, find and graph the solution of y squared minus 3y less than or equal to 0. So let's start by just following the rules we set ahead. So we're going to factor this expression once it's all on the one-hand side, so we can do that. We could say let's factor out a y as a GCF and get y minus 3, and that's less than or equal to 0. If we were to solve this, we would get y equals 0 and y equals 3 if we solved it like an equation. But it's clearly not that. These are just our critical points. So again, these are not our solutions anymore. These are the critical points. But it's like the solutions to the equation, or the roots of the equation. We then come up with our number line. We put these critical points on the number line. And then simply test these regions that are created. This is region 1, region 2, and region 3. Since this was a less than or equal to sign, these are definitely going to be closed circles. So we can already put them here. Now at this point in time, all we need to do is go ahead and test. So picking a point over here, I would pick -1. It's the smallest number that happens to be the left of this as far as its magnitude goes. So plug a -1 in up here. And what I'm going to tell you is that you should always plug it into the factored form because it makes it easier. When you plug a -1 up here, this just becomes -1. when you plug a negative 1 in, over here it's negative 1 minus 3, which is really negative 4. Well, negative times a negative is really a positive. So this is a positive region. I don't even care that when I multiply these two numbers here, I get positive 4. All that really matters is that when I multiply them, I get a positive result. In the middle region now, in here, I'm going to take a number like positive 1 and plug it in. And I can do this in my head. Plugging in a 1 here, this is 1. 1 minus 3 is negative 2. So I get 1 times negative 2. Well, positive times a negative. Positive times a negative is a negative in this region. And then finally, plugging in a number over here, let's plug in the number 4, which is next after it. So I plug in a 4, this becomes positive. I plug in a 4, 4 minus 3 is 1. Well, that's still positive. Positive, positive, multiplied, give you a positive. Now remember to note that if you try 0 or 3 into either of these, you're going to get 0, because these were the solutions to as if this were an equation earlier. Plug in a 0 here, this is 0 times negative 3, well, it's 0. Plug in a 3, well, this is 3 minus 3, that's going to be 0 times 3, which is still 0, so that doesn't work. So make sure you're only plugging in points in the regions, not these barriers we've kind of set up. Now we want to know, when is this expression less than or equal to 0? Well, things that are less than or equal to 0 are either 0 or negative numbers. So we shaded these in because it could be 0, or it could be negative numbers. Well, negative numbers exist in the region that's highlighted as negative, which is right here. So we shade that region. And because we're shading a region between 2 points, we know that it's going to be an AND statement, or we can say right away that y is in the solution between 0 and 3, inclusively, meaning including the endpoints, thus the less than or equal to signs you see here. Example 2 says, find and graph the solution of x squared minus 2x minus 8 greater than 0. So again, we'll approach this just like the last one. Let's factor it. We're going to get here is x minus 4 and x plus 2. So that gives me critical points at positive 4 and at negative 2. I go ahead, I make a number line to start right away. Here's my number line. First critical point, second critical point. And now I have to put open circles here because it's just a greater than symbol up here. Again, notice it's just a greater than symbol. So they're open circles, not greater than or equal to. And now we can test the point in this region, and in this region. So I'll test the point in all three of these different regions here to see what it gives us. So I'm going to test 0 in here. This is going to make this a negative. That'll make that a positive. Negative times a positive is a negative. So it's a negative in that region. The next region I'll test over here. This is negative 3. Let's try. Negative 3 minus 4 is negative 7, so that's a negative. Negative 3 plus 2 is negative 1, so that's also going to be a negative. And negative times a negative is a positive here. And then finally we have to test the third region, so we'll test the number 5. 5 minus 4 is 1. 5 plus 2 is 7. 1 times 7 is positive times positive, which is still a positive. And because this problem was wondering, when is this expression greater than 0, we're looking at the positive region, so we shade those. And those shade outward like this. So this answer now, we're going to see how it's an OR statement and not an AND statement. So we have x is in the solution set of x being less than negative 2 or x being greater than 4. Example 3, find and graph the solution of the quantity x minus 2 squared less than or equal to 0. Right away, well, this is just x minus 2, and therefore we have a double root or a double critical point. Okay, same exact critical point. So on our number line now, we only have one critical point at 2. So we have 2 regions to test, so let's go ahead and do that. If I test a number like 0 on the left-hand side in this region, plug in a 0 here and here, it's going to be negative 2 times negative 2. Negative negative is a positive, so this is a positive region. Then I go ahead and I plug in a point over here. Let's try a point like 4. 4 minus 2, 4 minus 2. Well, that's 2 times 2. Positive, positive is still positive. So it seems that both regions are positive here. Now, we wanted to know when this was less than or equal to 0, so we should have started by putting in a closed circle here because it's less than or equal to. But what numbers are less than or equal to 0? Negative numbers or 0. Well, these are both positive regions, so there's nothing to shade there. Since Since there's nothing to shade there, the only answer is 2. When x is 2, this is going to be equal to 0. It won't be less than 0, but it'll be equal to, and that works because this is less than or equal to 0. Now, let's think about this for a quick second. If this, instead of being less than or equal to, had just been less than 0, this would have been an open circle here, and there would have been no solution because both sides would have also still been positive. Again, it would have been everything less than 0. Well, nothing would have been less than 0 in that case, and it couldn't be equal to 0, so there would have been no solution had there been a less than symbol. Instead, we have the solution of x equals 2. We should also think about the possible case. Well, what if instead this had been greater than or equal to 0? If it were greater than or equal to 0, we wanted to know when is this expression positive? Well, it's always positive out here, and it's positive out here, and if it were greater than or equal to, that would be a closed circle. So it would be all real numbers then, if it were greater than or equal to. And finally, the last possibility, what if it were just greater than? What if the symbol had been greater than? Well, this would have been an open circle, but these are still regions that are greater than 0, right? These are positive regions, and we want to know greater than 0. So in this case, it would have been all real numbers excluding the number 2, which is a similar result to the problems we did when we found the domain of a fraction. Okay, so again, that would have been all numbers except the number 2. I find this to be an interesting way to approach one problem by looking at it in 4 different aspects and seeing how the problem shifts and changes. Example 4 says, find and graph the solution of w to the third minus 16w is greater than or equal to 0. Well, this problem is no different than the others. We're going to start by just factoring what we have here. So what we're going to do first is this. We're going to take a look and we're going to say to ourselves, all right, well, we've got this w that can come out, leaving behind w squared minus 16. But that can be factored even further into w plus 4 and w minus 4 because that's difference of 2 squares. Now this tells us that we have 3 critical points in this problem. W equals 0, W equals negative 4, and W equals positive 4. Again, from our t-chart. So we go ahead and draw a number line. On the number line, we're going to have negative 4 back here, 0 back here, and positive 4 back here. And again, remember to pick a point in each region to test into the factored form. So let's pick a point over here, like negative 5. Well, if I plug in negative 5 here, it's going to be negative 5 there. Then negative 5 plus 4 is going to give me negative 1. Then negative 5 minus 4 is negative 9. Well, negative times a negative is a positive, but then we times another negative, it's back to a negative. So this is a negative region. Then we go into the second region over here, and we say, well, let's pick a number like negative 1. We'll plug in negative 1, we're going to have negative 1 here. Negative 1 plus 4 is positive 3. Negative 1 minus 4 is negative 5. So it's going to be negative, positive, negative. When we multiply those 3 numbers, we get a positive region here. Then we can test a number like positive 1. We get positive, positive, negative. So this region becomes a negative. And then finally, again, we test a number like positive 5. This is positive, positive. 5 minus 4 is also positive. So this last region is indeed positive. So it looks like we have solutions that are alternating in signs, or regions that are alternating in signs of being positive or negative. So this really tells me that this expression is positive in some ranges or domains and negative in others. So if I were to graph this expression, it would be like it's above the axis here, and the graph of the expression is below the axis here, if I were considering w my independent variable. But this problem wants to know when the expression is above the axis or greater than 0. And that will occur in the regions that are positive. So that's our solution in this problem. Let's go ahead and actually write it up. They're going to be closed circles here, here, and here. And we're going to shade in the positive regions. So that means that there's a solution that is an OR solution, but it's kind of an AND solution also. Here's how we have to write this one. So W is in the set of numbers. Now it's between negative 4 and 0 inclusively, so I can write it like this. Okay, that's what's going on there. Or it's in the region to the right of 4. So or W is greater than or equal to positive 4. So again, this is representative of this region right here. This is like a little mini AND region, right? We have like an AND looking statement. Or is kind of like, remember the gap kind of represents an OR. or this portion, w greater than 4, greater than or equal to 4. In the final example, we're going to find and graph the solution of the following. H squared times the quantity h squared plus 9 greater than 6h cubed. Well, the easiest thing in this problem would be to multiply it out, because we need to get everything on one side. So let's move this over and multiply it out. Well, multiplying this out, we're going to multiply those two. We're going to get h to the 4th plus 9h squared greater than 6h cubed. We'll move the 6h cubed over by subtracting it, giving us h to the 4th minus 6h cubed plus 9h squared greater than 0. Now we can see that h squared can come out front, leaving behind h squared minus 6h plus 9. Well, this here, we clearly have the square of differences, or the square of sums, either way we think about it, but pretty much the same factor, h minus 3, which is really written like the following. So this tells us that we're going to only have two critical points. Again, one critical point is h equals 0, coming from the h that we factored out in front. Remember, we have to set h squared equal to 0, giving us h equals 0. Then here we have to set h minus 3 squared equal to 0, giving us h minus 3 equals 0 and h equals 3. So we've got h equals 3 and h equals 0 as our two critical points. Notice these would be like double roots in an equation, okay? Double roots or multiple roots. So we go ahead and draw our number line. Since it's greater than, we have 0 and 3, and we're going to have open circles at both locations for sure. And we're just going to simply test each region. And what we're going to notice is this. We go to the factored form and test the number like -1. Negative squared is positive, and then this squared is also going to be positive. So even though this is both negatives, they're both going to be squared to become positive. And what we might notice overall is that no matter what number we plug in, pick any number, you're squaring it, right? Pick a number like 2, you're squaring it. Whatever this turns out to be, you're squaring it. Pick a number like 7, you're squaring it. 7 minus 3 is 4. Whatever you get, though, you're squaring it. So you're always squaring these things, and then you're multiplying them. Well, anything squared is always going to be positive. So this is going to be positive, any real number at least. This is going to be positive here when you square whatever it turns out to be. And then a positive times a positive is always a positive. So it turns out that every region is positive. You can test any point. They're always going to be positive. And this problem wanted to know, when is this expression going to be greater than 0? Well, in all of these positive regions, but not at these locations because they're open circles. So we technically shade everything except for our critical points. So it turns out that our solution can be written as the following. H is in the set of numbers, or H is in the set of all real numbers, rather, except that H cannot equal 0 and H cannot equal 3. Your homework for this section is from the oral exercises and the written exercises in section 4.9.